This video covers section 4.4 on exponential and logarithmic equations. So we are going to use what we've learned about exponential and log functions and their properties to solve equations that involve variables in the exponent and logarithmic expressions. So we're going to start with the exponential equations. So here are a few examples of what these may look like. All of these equations involve at least one exponent that contains a variable. So there are two basic types. Depending on which type we have will depend on the method or the process we use to solve. So type 1 is the type in which the bases can be rewritten to be the same. So in this first example, 2 to the power of 3x minus 8 equals 16 is this type because 16 is a power of 2. So I could rewrite 16 using base 2. This last example is also this type. We have 27 to the power x plus 3 equals 9 to the power x minus 1. 27 and 9 are both powers of 3. So I could rewrite this expression to where the bases of the exponents match. The second type would be what if the bases cannot be rewritten to be the same? As in this problem, 4 to the power of x equals 15. I can't write 15 and 4 using the same base number. 15 is not a power of 4 and neither are powers of a different base. Same thing with this example, 40, e to the power 0.6x equals 240. On the left side here, the base of the exponent is this irrational number e, and I can't write 240, or even if I divided by the 40 first, I can't write that number using the number e. So we're going to start with case 1, if you can rewrite both sides using the same base. So if we can write our expression or our equation in the form b to some power m equal to the same base to some power n, then we can set the exponents m and n equal to each other. So for these types of problems, we will start by writing the equation in that form, then set the exponents equal to each other, and then solve for the variable. So the two examples that we looked at initially, and then there's another example here to show how this works. So we have 2 to the power 3x minus 8 equals 16. So in this case, the 16 can be rewritten as 2 to the 4th power. So since I can write both sides using the same base 2, I would do that first. So I have 2 to the 3x minus 8 equals 2 to the 4th. So once the bases are the same, that means the exponents must be equal. So 3x minus 8 equals 4. And then I just solve that equation. So I could add the 8 to both sides, and that would give me 3x equals 12. And then dividing both sides by 3 would lead me to x equals 4. So the solution set would just simply be 4. In part B, this was the other example we initially looked at, 27 to the power of x plus 3 equals 9 to the power of x minus 1. In this case, I can't write 27 as a power of 9, but I can write both of them as a power of 3. So I'm going to rewrite 27 as 3 to the 3rd. I'm going to put that in parentheses, and then I'm also going to put parentheses around this power, and you'll see why in just a second. The other side we're going to change also to be 3 to the 2nd. And again, put that in parentheses, and then put the exponent in parentheses. So now I'm going to utilize exponent properties of if I'm taking the power of something that has another power, the rule would be to multiply the exponents together. So we're going to do that next. So that's why I put parentheses around this quantity, because when I multiply by the 3, I have to distribute. So 3 times x plus the 3 times 3. So the new power becomes 3 to the power of 3x plus 9. Do the same on the other side. We would get 3 as the base. The new power would be 2x minus 2 when we distribute through the parentheses. Now we're going to set these powers equal. 3x plus 9 equals 2x minus 2. And then to solve for x, if I subtracted 2 from both sides, it would eliminate, 2x from both sides would eliminate the 2x and give me just 1x. And then at the same time, subtracting 9 from both sides would eliminate the 9 and end up giving me negative 11 on the other side. So my solution set for this problem would simply be negative 11. One more example of this type, we have 5 to the power of 2 minus x equals 1 over 125. So here we have a base 5. 125 is also a power of 5, so I can rewrite the right side using base 5. So you first probably should notice that 125 can be changed into being 5 cubed. Notice it's still in the denominator. So if I need to move it up to the numerator, it means I have to make the power negative. So shifting this 5 to the top changes the sign of the exponent. So now we have 5 to the 2 minus x equals 5 to the negative third. So we have the same base, meaning now we can set the powers equal. 2 minus x equals negative 3. So if I subtract the 2 from both sides, I'm left with negative x equals negative 5. And then divide both sides by negative 1 gives me x equals 5. So the solution set is 5. All right, in the other type of exponential equation, if bases cannot be rewritten to be the same, you will need to use logarithms to solve. So our process would be this. Start by isolating the exponential expression. So get the term that contains the exponent by itself on one side of the equation. Then we're going to apply either the common log, meaning log base 10, or the natural log to both sides. Usually you will use common log only if the base of the exponent is 10. Any other situation, we're going to use natural log. Step 3 then would be to simplify using the power property. Remember, we had exponents that contained variables at the beginning, and then we applied a logarithm, so that would then give you an expression, the log of something to a power. So that power property that we talked about in 4.3 can be applied. And then after you apply your power property, you should be able to solve for the variable. So the two examples that we saw on the first page. 4 to the x equals 15. We cannot write 15 as a power of 4, so we are going to use this process. This is a base 4, so we're going to take natural log. So natural log of 4 to the x equals the natural log of 15. Remember that the logarithm is a function. Okay, you're not multiplying by ln. All right, it's like taking the square root of both sides, right? Applying that function to both sides. All right, so to apply the natural log function to both sides means this left side now we can apply our power property and bring down the x to the front. So x natural log of 4 equals 15. Equals natural log of 15. And then to solve for x, we could just divide by natural log of 4. So we get x equals the natural log of 15 divided by the natural log of 4. Be careful in my math lab if they ask for an exact answer, this is what they're asking for. The solution set in exact form is natural log of 15 divided by the natural log of 4. If they ask for a decimal approximation, you would utilize your calculator, ask it to do natural log of 15, and then ask it to divide that by the natural log of 4, and it should give you the decimal value approximately 1.9534. So sometimes it is going to ask for exact, and other times it may ask you also to approximate. Part B was our second example that we saw in the beginning of this section. 40 e to the power 0.6x equals 240. So our steps here say isolate your exponential expression. The exponential expression is the e to the power. So to isolate it, I have to get rid of this 40. So I have to divide both sides by 40. So if I divide the left by 40, I'm just left with e to the 0.6x, and then 240 divided by 40 is 6. Base e would always mean natural log. Take the natural log on both sides. Apply that log function to both sides. So then, because the base of the natural log is e, and this is base e, remember it would simplify to just the exponent, 0.6x. The other side is just simply natural log of 6. And then to solve for x, we would divide by 0.6. So again, the exact value is the natural log of 6 divided by 0.6. And then if you enter that into your calculator, 2.98 0.63 would be your approximate value. This part right here is for the next problem. So two more like this. Part C, 10 to the power 2x plus 1 minus 4 equals 796. So again, this is one where we're going to have to isolate our exponential expression. Our exponential expression is 10 to the power 2x plus 1. So to isolate it, I have to add the 4 to both sides. So I get 10 to the 2x plus 1 equals 800 when I add 4 over. I can't write 800 as 10 to a power. So I'm going to take the common log of both sides. And I'm going to use common log this time because I have a base 10 exponential expression. So the log of the left equals the log of the right. I chose common log because it was base 10, so the base matches the base, meaning this will simplify to just 2x plus 1 equals log of 800. And then solving for the variable, first step would be to subtract the 1, so we would have this log of 800 followed by minus 1 when I subtract 1. Remember, this 800 is inside of this log function and the 1 is not. So you cannot write log of 799. That's not correct. It's log of 800 minus 1 equal to 2x, and then finally divide both sides by 2 to get your exact answer. So this entire expression divided by 2, or the approximate value of that using your calculator would be 0.95154. Our last example is a little bit harder, and the reason being is we cannot write 7 and 3 with the same base, meaning we have to use logarithms, and both of those contain an exponent. All right, so they're by themselves on each side of the equation, so we can start by just taking the natural log of both sides. Remember, anytime it is a base 10, we will use common log. Any other bases, whether it's e or any other number, we're going to use natural log. So the natural log of 7 to the x plus 3 equals the natural log of 3 to the 2x minus 5. All right, so now our power property applies. Again, I put this in parentheses. Same thing on the right side with the exponent, because when I bring down the power, I'm bringing down the entire expression x plus 3 in front of natural log 7. And on the right, we'll bring down the entire expression 2x minus 5 multiplied in front of natural log of 3. You need to put the parentheses around the power because our next step means we're going to have to distribute through the parentheses. So natural log of 7 is just a number. So we're just going to distribute it like we would distribute any other number. So x times natural log of 7 plus 3 times the natural log of 7 equals, do the same on the right, 2x times the natural log of 3 minus 5 times the natural log of 3. And remember, the goal here, we're trying to solve for x. So here is a term that contains x, and here is a term that contains x. So our next step is to rearrange your equation to put the x terms on one side and the terms that do not contain x on the other side. So I'm going to leave this where it's at, x natural log of 7. I'm taking this term and subtracting it over, so it becomes minus 2x natural log of 3 equals, at the same time, this term, because it does not contain x, moves to the right side, so subtracting it over gives me negative 3 natural log of 7, followed by the negative or minus 5 natural log of 3. So all I did here was just subtract this term over and subtract this term over, switch places. Once you've done that, you're able then to factor an x out of this left side, factoring out the common factor of x. The right side would not change. And then finally, to get x by itself, divide both sides by this entire set of parentheses. So our solution becomes x equals this negative 3 natural log 7 minus 5 natural log of 3 divided by natural log 7 minus 2 natural log 3. When you're inputting this into the calculator, if they ask for an approximate value, you would need to put parentheses around the entire numerator, divided by, and then put parentheses around the entire denominator. And then that should give you 45.0861. All right, so moving on now to logarithmic equations. All right, so these are equations that contain a logarithm. Maybe just a single log expression, maybe multiple log expressions. So examples would look like this. Log base 7 of x plus 2 equals negative 2. 7 plus 3 natural log x equals 6. Log of the quantity x plus 4 equals the log of x plus the log of 4. So there's a logarithm somewhere in the equation. Okay, again, there are two different types, and depending on the type will determine our process for solving. Type 1, the equation has a log expression and it has terms that do not contain a log, as we see in these first two examples. We have this log expression right here, log base 7 of x plus 2, but the other side is just a number. There's no log. This is also that type. We have the number 7. We have plus 3 times a log expression equals a number that doesn't contain a log. So you have log expressions and just regular numbers. Type 2 is the type in which every term of the equation contains a log, as we see in this third example. The log of the quantity x plus 4 equals the log of x plus the log of 4. Every single term is a log expression. All right, so depending on if you have some log expressions and some not, versus all log expressions will depend on how you solve. So for type 1, if there are log terms and terms that do not contain a log, we have to use the definition of a logarithm to solve. So in those cases, our first step is to isolate the log expression. In other words, rewrite the equation, condense any logs together, put the log expression on one side of the equation and any numbers that don't contain the log on the other side. So make it look like this. Once it looks like that, we're going to rewrite this log equation in exponential form. This is just the definition. If we have log base b of m equals a number c, this is, remember, equivalent to b to the power of c equals m. So we can write b to the c equals m from there. Your variable's likely to be contained right here in the expression m. Then we're going to solve for the variable. And in these problems, we have to check our solutions in the original. And we'll talk about what that really means as we do some examples. The issue here is that in my original equation, if your x is contained in here, remember log functions have a domain restriction, so we're just making sure that when we plug our x's back into the m expression, that we don't get a negative number. All right, so part A, the first example that we saw at the beginning, log base 7 of x plus 2 equals negative 2. This one happens to already be written with all the logs contained by themselves over here. One log expression equals a number. So we're already given our equation in this form. So we're ready to use our definition. So 7 to the power x, or negative 2, equals x plus 2. So 7 to the negative 2 equals x plus 2 is the definition of what this equation means. So 7 to the negative 2 is 1 over 7 to the positive 2 equals x plus 2. 7 squared is 49, so this is 1 over 49. We'll subtract the 2 over to that side, minus 2 equals x. And then using your calculator, 1 over 49 minus 2, you should get negative 97 over 49. It must be written as a fraction. Okay, if you type that in your calculator and it gives you a decimal, you have to convert it to a fraction, or else my math lab will not accept that answer. All right, so now we have to check. So when I say check, this is what we mean. We mean take this answer and come back up here and plug it into any expressions that contain logs. So if I plug negative 97 over 49 in here for x, so negative 97 over 49 plus 2, that gives me 1/49. That is a positive number, meaning it's greater than 0, so we can check that off and saying that it's a valid solution. If I plugged my answer into my log expressions and I got a negative number, we would have to throw it out and say we can't use that because you can't take the log of a negative number. So since it's fine when I plug it in, I get a positive result. My solution set is simply negative 97 over 49. Part B, 7 plus 3 natural log of x equals 6. So here, same type, but we need to isolate our log expression. So we need to get the natural log of x by itself on one side. So our first step of doing that would be to subtract the 7 from both sides. That would leave 3 natural log of x equals -1. Then I have to divide by this 3. So the natural log of x equals -1/3. All right, then I can use my definition. My base of the natural log is e. So we would write e to the -1/3 equals x. That's where this comes from. The -1/3 means 1 over e to the +1/3, but then the 1/3 power means the cubed root. So we could rewrite that answer as 1 over the cubed root of e. My checking, if I took that and plugged it back in, the only place I see a log is here, and it is a positive number, and this is just x, so when I plug in a positive, that's fine, so we're good. All right, here's a couple more. This one, log base 4 of x plus 2 minus log base 4 of x minus 1 equals 1. So here I have two separate log expressions that are being subtracted, but over here I just have a number that's not part of a logarithm. So this is still type 1 because we don't have a log expression on the right side. All right, so our first step is to condense. We have to bring all the logs together as a single log. So this is where the properties from section 4.3 are going to come in. We learned in 4.3 that if you're subtracting separate logs, then you can merge them into division. Log base 4 of x plus 2 divided by x minus 1, and then equals still to the 1 on the right side. So now we have a single log expression equals a number. So this is where the definition comes in. 4 to the power of 1 equals x plus 2 over x minus 1. That's how I get this line. Solving for x, we have to clear the fraction. So multiplying on the right by x minus 1 will cancel it, leaving just the x plus 2. On the left, 4 is going to get multiplied by the x minus 1. So I'm just multiplying both sides by x minus 1 to get here. Then distribute the 4. 4x minus 4 equals x plus 2. Subtract x from both sides is 3x. Add the 4 to both sides would give me 6. And then dividing both sides by 3, we get a 2. Don't forget to check it. Come back up here. 2 plus 2, that's 4. That's a positive number, so we're good there. 2 minus 1 is 1. That's also positive, so we're good there. So 2 is the solution. One more like this to show what happens if one of the solutions does not work. Log base 3 of x plus 6 plus log base 3 of x plus 4 equals 1. This is similar to the one we just finished. However, this time we're adding our separate logs, so to merge them together as one log, we're going to use our product property and bring them together as multiplication. So log base 3, and we're going to multiply inside the x plus 6 and the x minus 4 equals 1 on the right. Let's go ahead and do this multiplication. Log base 3, this just means multiply it out or FOIL. So x times x is x squared. The outer product is 4x plus 6x will give me a 10x in the middle, and then on the end plus 24. So we have log base 3 of x squared plus 10x plus 24 equals 1. So now we're ready to use our definition. This means 3 to the first power equals the inside. So 3 to the first equals x squared plus 10x plus 24. This is a quadratic expression, so to solve, we're going to set equal to 0 and try to solve by factoring or quadratic formula. 3 to the first is just 3, so we'll subtract it from both sides, leaving a 0 on the left. 24 minus 3 makes this now a 21. This expression factors into x plus 3 times x plus 7, giving me -3 and -7 as solutions. When I check the -3, plugging back in, -3 plus 6 is +3, so that's fine. -3 plus 4 is +1, so that's fine. So we can check this off as, yes, it works. However, when I check -7, -7 plus 6 is a -1. That can't be an argument of a log function. So we just throw it out, even though it also does not work here. As soon as you plug it into one expression and you get a no, then you can't use it. So -7 is not allowed because it's not part of the domain. So our only solution is -3. The other type of log equation was one in which every term of the equation contains a logarithm. So to solve these types, we're going to use what we call the one-to-one property. So our first step would be to condense each side of the equation to a single log. So write every log term on the left condensed to a log base b of some expression m, equals, and do the same on the right. Condense every log into a single log base b of n. Our one-to-one property says if log base b of m equals log base b of n, then m must equal n. So once I get it to this point, we can write m equals n. Now we can solve for the variable, and again we will check our solutions in the original equation. So log of x plus 4 equals the log of x plus the log of 4. Every term contains a log. The left side is already a single log. It's the logarithm of x plus 4. The right side we have to condense. So if we're adding separate logs, that means we could write the right side as log of the product. Bring these together and multiply. Log of 4x. So the log of x plus 4 equals the log of 4x means x plus 4 must equal 4x. And then to solve, we could subtract the x over, leaving 4 equals 3x, and then dividing by 3 would give me x equals 4/3. We would need to check 4/3 plus 4 is a positive number, 4/3 is a positive number, so everything checks out fine, so our solution is 4/3. All right, and then our last example, similar to the one we just finished, log of x minus 4 plus the log of x plus 1 equals the log of x minus 8. All right, every term contains a log. This time the right side is already a single log, so we leave that like it is. The left side we have to merge together. So again, adding the separate logs merges them together as the log of the product, x minus 4 times x plus 1. We'll go ahead and multiply x squared minus 4x plus 1x is minus 3x in the middle, and then minus 4 on the end. So the log of this expression equals the log of this expression. So we can set those two things equal. X squared minus 3x minus 4 equals x minus 8. Again, it's quadratic, so let's try to push everything to one side and see if we can factor. So if I subtract x, we get x squared, 3x minus x is minus 4x, and adding the 8 over, -4 plus 8 is 4, and then it would equal 0. This expression factors into x minus 2 times x minus 2, or x minus 2 squared. So setting that to 0 gives me the solution of x equals 2. However, when I check, 2 minus 4 is -2. We cannot have a negative inside of here. So if that was the only solution that I got and I checked it and it did not check out and is not valid, we just simply have the empty set, no solution. So that is the end of 4.4, and it is the end of what we are going to cover in Chapter 4.